Hey students, this is your Professor Omelianchuk, and today we're going to go over subderivation rules, or at least introduce one of them more formally that we've looked at already, conditional intro, and these are called indirect rules of inference because they're the ones that require you to make assumptions. Right, so I did show you a use of conditional introduction in the last lecture, and how it applied to the strategy of working backwards. And it may have been a little confusing, I understand. So we're going to go into more depth here about how to use this sort of rule. All right, so usually when students have to use rules that require them to make assumptions, they feel like a miracle is happening. Right? I mean, the big question is like, well, why did you assume that? How did you even know to do that? That just kind of popped out of nowhere. And so most students often find this to be confusing. People, when I see common mistakes is people making assumptions when they don't have to. You should only make assumptions if you have to. All right, and so I'm going to try and be more explicit about the when and whys. Okay? All right, so common mistakes I see often on the homework. I just want to go over this here, take some time before I get into the meat and potatoes of today's lecture. This is a common mistake that I see a lot. All right, and so I just kind of want to address these up in front so you don't make them again, right? Using conditional elimination and only citing one line, right? So you might have a problem that looks like that. All right, so there you have your two premises, and for whatever reason you may want to, you want to extract, like, you might think, oh, I really want that antecedent. So what I'm going to do is I'm just going to pull it out of there, right, and write it on line 4, and then just say to arrow elimination. Okay, but that's a mistake. That's just totally illogical, okay? It doesn't follow from a statement like, suppose this said, if it's raining outside, then it's wet outside. Therefore, it's raining outside. I mean, that just makes no sense, okay? So you do have to think logically about this. And so this is a common mistake I see. You actually have to cite 2 lines, right, when you use arrow elimination. So that's the first thing. And the only thing that you can eliminate for is the consequent, all right? So like I said before, right, it just does not follow from the truth that if P, then Q, that P is true, okay? All right, the same sort of mistake happens with biconditional elimination, which is just like conditional elimination. You have to cite 2 lines. So if you cite only 1 line, that's a mistake, right? So you might think, well, you know what, I really would like that GB out of line 2, and so let's just grab it, okay? And that doesn't work. That's also false. I mean, suppose this is saying, somebody's a bachelor if and only if they're an unmarried male. Now, that's certainly true, but it doesn't follow, right, that somebody's an unmarried male. It's just telling you the truth conditions about bachelorhood, right? So you can't do that, okay? That's a mistake. It just does not follow from the truth that P if and only if Q, that P is true. We know that biconditionals can be true if P and Q are false. So you can't do that. You have to cite 2 lines, right? So if you wanted this GB here, you'd have to use the A, B, right, on line 1, and then line 2 to get GB, okay? All right, another common mistake I see is using conjunction elimination and citing 2 lines, right? So, here's the thing. You might think, okay, I want to get this BK out of line 3. I also see a BK up here, which is in a conjunction. So when I do conjunction elimination, I'll just say, well, it's from lines 1 and 3. Okay, but that's a mistake. You actually can't reach in here and use conjunction elimination because this thing is a conditional. That's the main connective. Okay, so that's a mistake. We can't cite that. It's also ambiguous. I don't know which line you're really citing because, as you can see, conjunction elimination only takes 1 line as input, right, and spits out 1 line as output. Okay, so you would have to cite line 3 and do conjunction elimination to get BK. All right? So yes, yeah, just what I said. It's ambiguous. Which line are you citing? All right. Okay, so just to revisit the difference between rules of inference, the direct and indirect variety, we have direct rules of inference, and these are rules that do not require you to make any assumptions at all. All right, so we don't want to be doing making any assumptions when we're using the direct rules of inference. The only time we ever make assumptions, right, is when we're using an indirect rule, right? Those are the ones that require you to make assumptions to work out implications of the assumption in a subderivation. So we've talked about conditional elimination, not conditional elimination, conditional introduction a lot, right? And I've shown you some examples of this that look pretty complicated, right? But really it's very simple, okay? So if you're looking at this type of derivation where you need to derive FA arrow HA, and you don't have FA arrow HA in your premises anywhere, so you can't eliminate for it, right? What you need to do is make an assumption, okay? Suppose that FA is true, right? And so, and then work out the implications of that. Then you could derive HA, right? So we'll get into that why. Now, what this is saying here is like, hey, if you want to make a conditional that looks like this, P arrow Q, then this is what you got to do. You got to start a subderivation, assume the antecedent P, and then try to derive Q. And then on the last line of the subderivation, right, then you can derive, right, the consequent. Once you do that, you can discharge the subderivation, move back to the left, right, stop the indenting process, and then write P arrow Q, okay? So that's what we do here. We assume our antecedent, right? And so we start a new assumption. That's what this line means here. I'm starting an assumption. I'm starting a subderivation. Now I can work my way to HA using the familiar conditional elimination rule. So from lines 1 and lines 3, I can derive GA. Now the reason I can do that is that I can actually go up here, right, and get, right, I can use my premises. These are accessible to me, right? That is just fine, okay? It's only when you close off and discharge a subderivation that you are not able to access the content of it anymore. Okay, so that's the rule you need to understand, right? There's a lot, and I'll show you examples of why that matters and other problems. Okay, but anyway, all right. Now that I have GA, right, I'm trying to get HA. That's where I want to go. That's the subtarget inside of the subderivation. These lines, technically should be connected, but they're not, because this is a computer and a PowerPoint presentation, and that's just how the thing works. Okay, so now that I got GA, right, I can use line 2 and line 4 and get HA, right, with arrow elimination. Now I have derived, right, the consequent of the conditional that I'm wanting inside of my subderivation where I assumed the antecedent. Right, so now that I've been able to do that, I've satisfied the requirements of this rule, and now I can stop the subderivation. I can discharge that subderivation, and now I can write FA arrow HA, right? And that comes from lines 3 through 5. That's 3 through 5 because that's the subderivation, all right? All right, so that's how it works. Now, this is a famous argument form. I kind of get into how I applied this argument form in real life in a paper I wrote, and I'm not going to go over this section of this. You can look at this in the slides if you'd like. What I'm going to do is just skip right over to the argument form, all right, and just take a look at it, right? This is an example of a hypothetical syllogism. It basically has this pattern. Now, it doesn't have to have this many premises, right? But the basic idea is you go, okay, if A, then B, B, then C, C, then D, D, then F. Okay, so therefore, if A, then F, right? It's kind of this baby step style argument, all right? So hypothetical syllogism, right, is the sort of argument, right? It's going to make use of the content of conditional introduction because we think, well, what if A were true, right? Then you could follow the logic of these premises, right? And then deduce that FA would be true, right? That's why it's a hypothetical. It's one of those, well, if A were true, then F would be true, right? And so you can kind of see how this works, right? This is just going to make use of the arrow introduction rule here. And what we're going to do is, okay, so I'm going to derive A arrow F, right? AA arrow FA. And so the first thing I want to do, that's what I'm going to want on my last line. And so what I'm going to do is I'm just going to assume my antecedent, right, which is AA, assume that. And then I'm going to try to derive FA, okay? I'm going to get FA on the last line of my subderivation here. And basically what this becomes is just an exercise of using conditional elimination inside the subderivation, right? So there's A. And then with lines 1, line 5, right, I can derive BA. And then with line 6 and lines 2, I can derive CA. Right, with lines 3 and line 7, I can derive DA. And then finally, with lines 8 and lines 4, I can derive FA. Now I got FA as the last line on my subderivation. So this line is indicating a subderivation. Right, I can discharge that now because I've satisfied the requirements of the rule. I can move back to the left, right, oops, and then write AA arrow FA. And I'm going to cite lines 5 through 9. Notice that there's a little dash here, right? There's a little dash. Okay, that is signifying a through, 5, 6, 7, 8, 9, right? And then I write arrow introduction because I'm creating a conditional, right? So in these cases here, I'm eliminating a conditional. Here, I'm creating one, right? And so that's the problem, okay? All right, so we have a rule here, conditional introduction, that says if it can be shown that Q follows from P, then we can say that if P is true, then Q is true, which is exactly what this is saying. All right? Okay. All right. So what we're going to do here is derive this problem. All right? And this is an example of what I call nested subderivations. Right? Nested subderivations are derivations that are inside other subderivations. Okay? So if you're going to look at our target here, I mean, all we have is one measly little premise here, IA. But the thing that's nice about that is that is the innermost consequent of the formula that we're trying to derive. Right? So what we're going to do then, right, is we're going to look at our target and we see this is one big conditional. Right? So what I'm going to do in order to derive this is that I'm going to just start out by assuming my antecedent. Right? That's what I always do. Whenever I'm introducing a conditional, I assume the antecedent. Now that means that I have to start a subderivation, so that's what I do. I draw a little line, and I indent to the right, and write FA. And I like to mark my assumptions for the reason why I'm doing so. So I do a little slash arrow introduction, right? So then, now what do I do? Okay, well, what I gotta do now is get this whole thing on the last line of this subderivation that I started right here. But notice that this whole thing is a conditional. So here's the antecedent of the conditional I need to get, and then here's the consequent. So I gotta create this, and so what I'm gonna have to do is introduce an arrow. I'm gonna have to use arrow introduction, and arrow introduction tells me to assume my antecedent. So that's what I do. So I just start another subderivation inside this subderivation. There's nothing scary about this, right? Students often go, boy, once you start working your way in, you get really committed. Well, that's true, but you're doing this for a purpose, okay? So now my goal inside of this subderivation is to get this thing on my last line, right? I need to get that on the last line of this subderivation. Now I've assumed that for arrow introduction too, so that's why I gotta do that. Now, what I'm trying to get on my last line, well, it's another conditional, all right? So you can kind of see where this is gonna go, right? I have to create this conditional, so I'm gonna have to use arrow introduction, which tells me to assume my antecedent. So I make another assumption, right? So now I'm like 3 deep, right? I'm like 1, 2, 3, right? But here's the thing. Now that I've assumed this, my goal is to put IA, right, on the last line of my subderivation here. Now you might be wondering how I'm gonna do that. Well, I can access my premise. That's accessible to me, right? In fact, this assumption is, and that is too, and this is, right? None of this stuff is closed off to me, right? Now, what I'm going to do, how I'm going to do this is I'm actually going to use what's called the repetition rule, right? In order to bring the IA inside of this subderivation, I'm just going to repeat the premise, and that's fine. I can do that, all right? This is actually a rule of inference. I didn't go over this in the direct rules of inference lecture, so I'm going to add it to your repertoire of rules right here. This is just the repetition rule. So if you have P on a line, well, then you can repeat P on a subsequent line, right? And so we mark repetition with R, of course. And so now I have, right, the consequent of the conditional I wanted on the last line of this subderivation. And now I can stop the subderivation. I can discharge it. And then on line 6, move back to the left into this subderivation here and write HA arrow IA. And that's going to come from lines 4 through 5, arrow introduction. Right, so now this subderivation is closed off to me. I can't access anything in here anymore. But you know what? I don't need to, because my goal all along with this particular assumption was to derive this so that I create this piece here. All right, so that's what I've done that. I got this on the last line of my subderivation. I've derived this from that. And so I'm going to discharge this subderivation here, move back to the left on line 7, and write GA arrow and then HA arrow IA, and that comes from lines 3 through 6. 3 through 6, arrow introduction, right? Now, this is what I wanted on the last line of this whole long subderivation that we started on line 2, right? And so following the rule again, I move back to the left. I discharge the subderivation. Right now, on my last line, I don't have any subderivations to deal with, and I create my arrow from lines 2 through 7, right? Because I satisfied the conditions of the rule, and I can now write the target. Okay, so that's an example of a problem that uses nested subderivations, where you have subderivations inside of other subderivations. And it looks kind of complicated and kind of scary, but it's actually really quite simple. All we're doing is just following the rules given what our target is demanding us to derive. And what we're doing is a kind of construction project. We're putting this thing together using using the rules that are able to build this connective, right? And that's basically all we're doing, okay? All right, so I want to talk a little bit about biconditional introduction and ring elimination. You'll notice that these two rules take as input two conditionals each. So biconditional introduction wants you to have two conditionals that have this kind of pattern, right? P to Q and Q to P, then you can write P double arrow Q. Oftentimes you have to create both of the conditionals, okay? Same thing with disjunction elimination. You have to create both of the conditionals, all right? The P arrow R and the Q arrow R. Sometimes those just aren't given to you, right? So oftentimes when you have to use these rules, especially on the last line of your derivation, you're most likely going to be doing arrow introduction. Okay? Arrow introduction goes along with these rules. That's what I'm trying to say. So I encourage you to work on these practice problems, right? This is the one. This problem right here is much like the problem we just did, right? So you're given one premise, but notice that it's the innermost consequent, and then you start off by assuming A, you assume B, you assume D, repeat your premise under the subderivation where you've assumed C, and then you kind of just work your way out, all right? And I want you to get used to that idea of nested subderivations, okay? In this case, you have to create two conditionals and then conjoin them together. Assume FA twice on two separate occasions, right? Here you're going to have to create two conditionals again to create this biconditional. So you'll have to do conditional introduction twice on two separate occasions to get that. Okay, this is going to be a disjunction elimination type of argument. All right, and you'll have to do disjunction introduction in order to satisfy the rules of disjunction elimination. All right, This one is also complicated. That's another disjunction elimination problem. And this is going to be, I believe, this is also going to be, I think, a disjunction elimination problem. So you can see the answers to these problems on this link, right? And that will, I think that is all I have for you today. So yes, that's it. And so if you have questions, shoot me an email. We'll talk during Hangouts or post something in the discussion section of the website. And I should say, will talk to you later.